Hello everybody. Previous video was about Gauss law, and it said law, but it's not actually law. The law is something like is very fundamental things. This Gauss law is derived from the more fundamental physics equation, and that's the fundamental logic equation provided everything necessary to have a Gaussian equation. Gaussian equation in the previous divergent D equals Q. This is charge density, or surface integral of D by ds vector equals volume integral q dv. Okay, so please look at the previous video if you have still question about this Gauss law. Okay, so we explained where this Gauss law come from. It's come from very fundamental law, which is Coulomb's law. When charge, say Q, and another charge E, there is a force acting. So Q, and you have a E. This force is going to be constant, some kind of constant, Q, E, and R square. R is a distance. Okay? And this is like Coulomb's law is like a Newton's law. This charge act on this charge. Mysteriously, they are linked together. Okay? And distance matter. Like gravity, you have a gravity, sun, and earth, and distance. This act together. It's the same gravity force. Let's see, this is Fc. F equals gravity constant, mass, and R square. Okay, so Newton and Coulomb's law are at the same level, the point-to-point physical effect. So if you have another charge here at the different distance, okay, then this distance goes into this equation, then force is different. Okay, now Coulomb's law is quickly evolving to the field theory. Now, what is field theory? It's like a vector all over. Okay, what kind of vector all over? When you have a charge Q, then it's create a field, vector field, and this vector field interact with charge E, then generate force. So it's not like directly this large Q is acting on small q, E. It's a large Q generate field. It's called electrical field, right? So force becomes electrical field times E. Okay, whatever the vector field times this charge is going to be the force. Why you do this? Okay, because field theory is very convenient to use, and that's evolving to Maxwell's equation later. Okay, so what is this field then? Is it really existing in the vacuum space? Well, actually, only thing scientists can say is you assume it exists in vacuum space. It doesn't conflict with any other physics law. Okay, so we use it, and when we use it, we found it mathematically much easier to deal with instead of dealing with individual charge particle, okay, by the distance. So then why we didn't do Newton into the same thing, gravity field all over? Okay, Einstein didn't do that. Einstein said gravity is different. Gravity is, he used the skew in the space, and that's getting to the general relativity theory. Means when the space is, say, stretched here because of the large mass, the space is skewed, it's stretched here, then this vector field become eyes here. This direction is same eye, but this eye length is different because space stretched. Okay, so the vector theory, you cannot use the vector theory you learned. You have to use this next level mathematics, tensor. Okay, so Einstein said we can assume this. Well, it's just like a Coulomb's field theory. There's a vector field E. We can say gravity field. We can do that somewhat, but it doesn't go anything beyond it. The other physical phenomena come from this Einstein's relativity assumption. And then you ask yourself, what do you mean space is stretched? I think vacuum has nothing in it. Can you stretch that nothing? I mean, right? So we don't know. The scientists actually don't know. It just assume vacuum space stretched, then relativity theory can be made, and that's explain a lot of stuff. Okay, same thing. We have electrical field, and that's explain a lot of things. So if you compare this electrical field Ke Q R square E, right? So this is E is K E Q R square. So this is the electro vector field. It's in the uniform space. We assume the Q is creating this radiation vector field. Okay, so what's happened is D is defined as epsilon E, right? So it's going to be epsilon K E Q over R square. Okay, now if its vector field is going out from the Q uniformly in the space, we take a integral, right? Surface integral is going to be simply 4 pi a square. A is this radius, say r square, right? And d Okay, that's going to be total charge Q, right? So D equals Q over 4 pi r square. We define D. We haven't defined D yet. D is only this. Okay? So, what's happened is let's see. You compare this with this one. E equals KE Q R square. The difference is this epsilon, this, right? So epsilon KE equals 4 pi 1. That means Coulomb's constant is 4 pi epsilon 1 over. So this is the equation. Okay. So Coulomb's constant is defined by this electric constant. Okay. Why we became like this? Because we assume Gauss law, but the actually story is other way around. This is a definition, okay, and we define constant this way, then it's conveniently become this Gauss law. Okay, so what do you mean we define this way? This one, you define the constant to be convenient. So D, divergent of D become Q. The Gauss law is based on two things. One is Coulomb's law, and another thing is constant definition. Now you have to know, in different old physics book, they don't use metric. So what's happened? This constant equation looks different in order to adjust it. Okay? But in a metric system, if we define constant this way, Coulomb's constant this way, then it becomes nicely D, flux, electric flux, is defined just like Gauss law works. This is important. You have to notice, right? So Gauss law, based on these two assumptions, but there are more underlining assumption. For example, you have a Q. How do you know D goes out uniformly? Well, this is just assumption, right? In the real world, all the D come out from this side and not on this side. But it's kind of strange. You have to explain the physics. It's supposed to be symmetric. Well, who said this world is symmetric? Well, the symmetric is implied physics law. If D come out from Q, the D, what is D? D is E, right? Electrical field. Now, how comes we have two different things? Okay, think about this. Oh, underlying assumption is flux radiate uniformly. Okay, now what's the difference between D and E? What is this stuff? So this one is actually the material constant. And suppose you have a Q and it's acting E, the force is determined by Coulomb's law. Suppose you have different material here, ES, on the way. So flux go through this, or this material surrounding this E. The even same distance, the electrical field here is different because electric field is reduced by this polarizing material. Okay, but the D is nothing to do with material. It's just a physical configuration. If it's R, you get the same D here, same D. But electrical field, actually, you get E dash here because of this material going through. The electrical field becomes weaker sometimes. Okay, so there are two different flux. You're talking about two different flux. Now, in the Maxwell equation, you introduce another flux called magnetic flux. Suddenly, vacuum space becomes so busy. Not only gravity, it has electrical flux and D flux and magnetic flux, measured by Henry H, and B, just like a D, there's a magnetic flux. So what are those flux? There's so many flux going around in the vacuum space. Well, as I said, we use that only because having those in a vacuum space, it doesn't conflict with other physical law or physical phenomena. In fact, we already know magnetic field. It actually doesn't exist. Magnetic field is just another expression of electrical field. How? Well, it's a relativity effect cause magnetic field. The magnetic force, okay? Relativity causes magnetic force. And that's why we define magnetic field. But we created magnetic field to explain magnetic force, but actually magnetic field doesn't exist. It's mathematically easier to incorporate and calculate all the forces around. A very good example is the relativity effect can be calculated without relativity theory, which is magnetic force. Okay? And Maxwell can make it very symmetric, nice equation for all the electromagnetic field forces. Okay? It's just mathematical tool you have. But electric field, is that mathematical tool? We don't know. There is something there, but when you declare it's a vacuum space, it's a vacuum definition, nothing. But even worse, the Einstein said, oh yeah, that's space, vacuum space stretch. I mean, come on, right? So we don't know what's there, but we define those fields, use mathematics to derive many things, and that's match up with the observation. So why not using it? Got it? So that's all for today. If you like this video, please subscribe and wait for the new video.